Hello and welcome. Today I'll be describing the dual nature of light as a wave and a particle. In previous videos I've talked about light mostly in the wave sense, but light can also be thought of as being composed of particles. So Newton, when he was doing his work, he believed light was made out of particles. I can't remember the exact reasons, but that was his philosophy. There were others during his time and during the next century and the next century after that thought light was definitely just a wave, not a particle at all. Well, Einstein, he came around in the beginning of the 1900s and he explained something called the photoelectric effect. And this described light as no doubt it has to behave somewhat like a particle. So to explain the photoelectric effect, imagine we have a block of metal. Let's say we have a block of gold, okay? This is our block of gold right here. And imagine we shoot light at it with a certain wavelength. We'll call it lambda 1. Remember, wavelength is usually denoted by the Greek letter L, lambda. So we have light coming in of wavelength lambda 1, and it was known that sometimes if you get light hitting the metal, it would eject electrons, right? And the energy of the electrons had a certain dependence depending on what kind of light you put in. So the formula for a kinetic energy of any particle is half mv squared. So if you measure so at different times, depending on the conditions of light you put in, the kinetic energy of the electron coming out would be different. Okay? So we're going to do 4 thought experiments upon this is a block of gold. We're going to shine bright blue light on the gold. We're going to shine dim blue light on the gold. We're going to shine bright red light on the gold. And we're going to shine dim red light on the gold. Now, I'm talking very generally here. If you shine blue light on gold, you might not get electrons out. But the point I'm trying to get across is blue light. In another video, I talked about blue light has a higher frequency than red light. Okay? And blue light also has a shorter wavelength than red light. So, if we shine bright blue light upon our block of gold, it was found that you would get a lot of electrons out with high kinetic energy, say. So, for instance, you would get about 10 electrons out with some kinetic energy. The amount of kinetic energy really doesn't matter. You just get some out. And as you make the light dimmer and dimmer, you still get electrons out, you just get less and less. So if you have very dim blue light, say you might get 1 electron out. Now, you perform the same experiment with red light. Even if the red light is just as intense as the blue light, just as bright, say, as the blue light, it was found that you get no electrons out. And you dim the red light down, you still get no electrons out. And so this was weird. With dim blue light, you get electrons out. But if you shine really, really bright red light on it, well, then you get no electrons out. Well, now that does not make sense in the case of a wave, because a wave carries energy, and a bright wave you would expect to carry more energy than, a dim wave. A bright wave would, have a high amplitude. It would look something like that, say. Dim light would, have a small amplitude. It would look something like that. So this wave up here has more energy than this wave down here. But the thing is, blue light, whereas blue light may look something like this wave right here, we'll say this is blue light. Red light, the wave for red light looks something like that. So you can see the wavelength is longer in red light. Call it lambda red, lambda blue. So lambda blue is smaller than lambda red, and so it's the opposite thing for frequencies. Remember, frequencies are denoted by nu. So the frequency of blue light is greater than the frequency of red light. And now around Einstein's time, it was being found out that indeed light does act like particles, and each particle of a certain frequency or wavelength of light was related by so the energy of a single photon, E, was equal to some constant times the frequency of that light. And so if you accounted for the number of photons, well, you would just multiply it by the number of photons. So this formula told us that blue light, one photon of blue light, has more energy than one photon of red light, is what this formula said. And now, if you do this experiment, you find that, well, due to conservation of energy, you get some kinetic, so you have a particle going in, which has some certain energy, and then you have an electron going out, which has to have the same energy, because energy is conserved. That's one of the precious laws of physics. We can never break that law unless we can't explain it any other way. But let's say the conservation of energy is true. So to conserve energy, you have to have the kinetic energy plus some other quantity. Call it W. Now Einstein found this out. Einstein called W the work function. Work function. Because depending on the, well, if the work function's less, like say, gold might have a large work function, but then silver might have a smaller work function. Heisenberg, quiet. So if you shine light of the same sort of light upon gold, well, if gold has a higher work function than silver, well, the kinetic energy of the electrons coming off in gold should be smaller. And now, so this is the equation for the photoelectric effect. This equation explains the photoelectric effect. So photoelectric effect. And now, if you shine red light, since red light has a different frequency, you're not, let's erase this N for now. Because imagine we're just thinking about one photon and one electron coming out. So if the frequency of your light was not great enough to surpass the work function, well then you get no kinetic energy out. The electron won't get kicked out of the atom, so to speak. So that's how Einstein showed that light has particle-like properties. And he also found out that if you have the sun and, well, this was his argument that space is curved, but you can think of it as photons are particles. Well, he showed that light is bent, and you would expect particles to be influenced by gravity, but not waves. So that was another argument for why light can be thought of as particles. And those particles of light, Newton called them corpuscles. Corpuscles. Corpuscles of light are photons. So that explains a little bit about the dual nature of light as a wave and as a particle. I hope you found that interesting, and have a good day.